So here we go with the free response section. Sodium carbonate gives you the formula weight, is used as a standardized hydrochloric acid solution. You may use the reaction for both A and B. 53 grams of sodium carbonate are reacted. How many moles of hydrochloric acid are required? So the steps to these problems are always write the balanced chemical equation, which in this case is given to us. Step number 2, when in doubt, convert to moles. Sometimes it will include or need the periodic table to go for grams to moles. Sometimes it will be the molarity triangle, where it's molarity equals moles divided by liters. Step number 3 is the mole-to-mole ratio from the balanced chemical equation, and then step number 4 is to convert to whatever asked for units. In this case, there aren't any other special asked for units, it just asks for moles, so you'll just be done after number 3. It's a nice type of problem to start with here because you're already given the balanced reaction as well, so really you're just going to do steps 2 and 3. So we have 53 grams of sodium carbonate, Na2CO3. Multiply sign, put a line, Na2CO3 in a position where it's going to cancel. Its grams are 106, and there's 1 mole in that amount or grams of sodium carbonate. So that will do my converting to moles, and you see the numbers are really nice. 53 divided by 106 is 0.5 moles. And then next we need to do the mole-to-mole ratio, and in this case put Na2CO3 in a position where it's going to cancel, and there's a 1 in front of that, and it asks how many moles of hydrochloric acid are there, and hydrochloric acid would have a 2 in front of it. So 0.5 times 2 gives you 1, so 1 mole would be produced of the, would be required to do the reacting. Question B, if the titration required 500 milliliters of hydrochloric acid solution to reach the endpoint, what is the molar concentration? So now we're told it took 500 milliliters of the hydrochloric acid, same equation, so step 1's done. And so now, since we're given a volume, we probably think we're going to use the molarity triangle right away to do step 2. So it tells us that the we have this volume of hydrochloric acid, and it asks what is the molar concentration in the end. So we'll probably use that here actually for the units. Since we know that it took 1 mole of hydrochloric acid to do the neutralizing, we have 1 mole, we have 500 milliliters, moles and liters. We could find the molarity. So the molarity or the molar concentration would be moles, 1 mole, per liter. 500 milliliters is 0.5 liters. So I think it comes out to be a 2 molar solution, 1 divided by 0.5, right? So a 2 molar solution would be our units, moles per liter, or capital molarity. Question C. Calculate the mass in grams of potassium carbonate required to react with 25 milliliters of hydrochloric acid solution in the following reaction. Step number 1, balanced chemical reaction, done for us. Step number 2, convert to moles. So we're given a volume and we're given a molarity. If you have a volume and you have a molarity, you can find the moles. So the moles would be equal to the volume of 0.025 liters times the molarity, which is 0.5 moles per liter. Multiply those two together and we'll have our moles of hydrochloric acid. Step number 3, mole-to-mole ratio, so put your HCl in a position where it's going to cancel. And then we want to know potassium carbonate, so put K2CO3 as your new set of units. For every 1 K2CO3, there's 2 HCl's. And then last step, convert to the asked for units, and in this case it's asking for the grams. So last step, put a multiply sign, put a line, put moles of K2CO3 in a position where it's going to cancel. They give us the formula right here. So there are 138.21 grams in 1 mole of K2CO3. Let's multiply those all together at once. 0.025 times 0.5, enter, divided by 2, right here, enter, times 138.21, enter, 0.863 to 3 sig figs. 0.863 to 3 sig figs of grams. Question D. Rewrite each of the following reactions as net ionic reactions. See the front page for information on acid and base strengths. The symbol aqueous indicates dissolved aqueous solution of ions. Calcium hydroxide is told that there's a solid there, so don't break that up. CaOH2. Solids never break up. And then HBr is aqueous, so 2H plus and 2Br minus. Notice how the 2 distributed to each one of those ions. Calcium bromide is aqueous, and you also know from your solubility rules that all bromides are soluble, right here. So split that one up into Ca plus 2 and 2Br minuses. And then water is a pure substance that is molecular, and so you leave that together. This would be the complete ionic solution or equation. The 2 bromides would cancel, and it would give you the net ionic equation. For this one, balance the reaction first, it says. I think that's balanced. 6 bromines, 3 irons, 2 aluminums, 2 aluminums. It tells us that this is aqueous, so we split it. Whoops, this should be a 6. The aluminum stays together because it's a solid. This one is aqueous. Notice how the bromines would cancel with the bromines. And then we have the underlined species right here giving you the net ionic equation. And the last one, split it because it's aqueous, all nitrates are soluble. Aqueous. The NAs would cancel, the nitrates would cancel, and the remainders would be our net ionic equation. Last page. Write the complete balanced molecular equation for the acid-base reaction of hydrochloric acid with strontium hydroxide. Both aqueous, it says. And it says just the molecular equation, so swap the cations. Hydroxide's -1, hydrogen's +1. Strontium's +2, chloride's -1, so you'd need 2 chlorides right there. Notice how I referenced the strontium right here in group 2, +2, chloride being -1, and you'd need 2 of the -1 things to make sure that you balanced out the +2 of the strontium. To balance this, I think you need a 2 here, and I believe a 2 right here. That's the molecular equation balanced. Write the complete molecular equation for the reaction. Aqueous potassium hydrogen sulfite with hydrochloric acid. Big bell should go off right away. Ding, ding, ding. Hydrogen sulfite. That's going to be a gas-forming reaction with acid. K and H switch, so you get KCl, positive 1, negative 1, positive 1, negative 1. And then you get some of this H2SO3, which immediately decomposes to give you water and the sulfur dioxide gas. And so technically you don't even write that. For the molecular equation, you can just leave it like this. Complete the balance following molecular equation. Copper sulfate, which has copper in the +2 ion state, and it tells us that copper is reduced and magnesium is oxidized, which means copper and magnesium must swap places to get magnesium to be oxidized to a charge. If I don't know what charge magnesium would be charged or oxidized to, look on the periodic table. Notice it's +2 right here, so magnesium would go to +2, and then that means that copper would be reduced to copper 0. Since magnesium is +2, it would fit nicely with the SO4, and so you'd write it MgSO4, and you'd just write copper alone by itself. It just wants the molecular equation, so you wouldn't write it like this or like this. You'd just swap the two cation ions there. Oxidize Mg to +2, reduce copper to 0. Last one. In a lab test, you're required to create 0.5 molar sodium hydroxide. Calculate the mass of solid sodium hydroxide needed to produce 1.5 liters of a 0.5 molar solution. The formula weight is 40 grams. Molarity is equal to moles divided by liters. So if I'm looking for the number of moles, moles are equal to the molarity, 0.5 molar, times the liters, 1.5 liters. 0.5 times 1.5, I believe that's 0.75. And then that's the number of moles. And I want to convert it to grams. Grams in a position where it's my new set of units. Moles in a place where it's going to cancel in 1 mole. There's 40 grams. That's what this is. That's from the periodic table. 0.75 times 40, I believe, is 30 grams. Did I do that math right? Let's check to make sure. Since I'm on camera, I probably made a mistake. 0.5 times 1.5, enter, times 40, and I ended up with 30 grams. To 3 sig figs, it would be 30.0, but if you just put 30 point, you'd be to 2 sig figs, which was what the 0.50 molar is. Letter G, calculate the number of grams of solid 2-sulfate copper pentahydrate needed to prepare 500 milliliters of a 0.25 molar solution. They make it tricky here by giving you copper sulfate dot 5H2O. This is a hydrated compound, and when you add up the molar mass or molecular mass or formula mass of this, you have to take into account the 5 waters that are attached to the structure. So adding it up on the periodic table, copper is 63.54. I'm going to round it to 55. Sulfur is 32. Oxygen is 16 times 4. Water is 18, and I need to multiply that by 5 because there's 5 of them right here. We need to add all of that together to get our molar mass of the copper sulfate. So 63.55 plus 32 plus 64 plus 18 times 5. I end up with about 250. I'm going to round it to that to make it easy. 250 grams in 1 mole of the copper sulfate dot 5H2O. This is called pentahydrate because there are 5 waters, 5 meaning penta. So calculate the number of grams, and it says 500 mils of a 0.25 molar solution. So we can find the moles first. Moles would be equal to my molarity, which is 0.25, times my liters, which is 0.5 liters, because the 500 milliliters has to be converted to liters. So 0.5 times 0.25 is 0.125. And then we would take that moles and we would multiply it by 250 grams in 1 mole. That's the number I added up right here for the number of grams in 1 mole. 0.125 times 250 ends up being 31.25 grams. would be needed to make that solution. 31.25 is 4 sig figs. I think we only have 2, so we'd actually round it to 31 grams in sig figs. Bonus question, calculate the mass in grams of potassium carbonate required to react with 5 milliliters of 0.25 molar hydrochloric acid solution in the following reaction. Step number 1, balance the reaction. Step number 2, when in doubt, convert to moles. So we have 0.25 molar, multiply it by our liters, 5 milliliters, 1, 2, 3, 0.005 liters. That's my number of moles of potassium carbonate. Potassium carbonate would go in a position where it's going to cancel, K2CO3, 1, and it asks the mass. Oh, this says it's hydrochloric acid solution. I'm sorry, I put K2CO3 right there. It's hydrochloric acid solution right here, 0.5 milliliters of 0.25. So put HCl, let me rewrite this. 0.25 times 0.005 is 0.00125 moles of the HCl. Put HCl in a position where it's going to cancel, and then put our potassium carbonate as my new set of units. There's a 1 in front of the potassium carbonate, a 2 in front of the HCl. That gives me my moles of K2CO3. And then it asks what is the mass in grams, so I need to convert this from moles to grams, and it gives me the formula weight of 138.21 right here. So take this number, 0.00125, divide it by 2, and then multiply it by 138.21, enter, and so my mass in grams of potassium carbonate needed would be 0.08638 to 3 sig figs. It would be 0.086, well, 0.0864 grams, because I'd round up.